Okay, so lecture 5. So we'll do a homework problem. This is in section 1.3, number 2. And we have the numbers, let's say A is 4,534 and B is 1,876. Okay? So if we apply the Euclidean algorithm to find the greatest common divisor, it's just successive divisions. So if we take 4,534 and divide it by 1876, I think that goes 2 times.
Yes, with the remainder of 782.
Okay, so this is times 2 plus, and what is the remainder?
782.
782. Okay. Then we take 876, divide by 782. I guess that goes 2 times. And what is the remainder?
312.
Okay. And 782, lots of 2's here, is 312 times 2. That's 624. So it looks like the remainder is what, 168?
58.
Okay. 312 is 158 times 1 plus the remainder of 154.
154, yeah.
158 is 154 times 1 with a remainder of 4. 154, if you divide it by 4, you have a quotient of 58.
38, I think. 38.
38. And what is the remainder?
2.
And if you divide 4 by 2, you get 2 and a remainder of 0. So the last non-zero remainder is 2. So the GCD of 4534 and 1876 is 2. So then the problem is to find X and Y such that 2 is this linear combination 4534 times X plus 1876 times Y. And you can always do that by working backwards from the Euclidean algorithm. So let's do it. Let's see. So see if I can get it all over on this side of the paper. 2 is 154 minus 4 times 38. But 4 is 154. Sorry, 4 is 158. No. Just write it down correctly. So 2 is 154 minus 4 times 38. But 4 is 158 minus 154. So I can substitute that for 4 times 38. What do I have? I have 154 minus times minus is plus 38 times 154. So that's 154 times 39 minus 158 times 38. Right? So if I'm doing my arithmetic correctly, all I did here is interchange, just expand and collect terms. Minus 158 times 38 plus 39 times 154. So let's see, I've used this equation and this equation. According to this, 154 is 312 minus 158 times 39 minus 158 times 38. So what do I get? I get 312 times 39 minus 158 times 39 minus 158 times 38. So that's minus 158. 39 plus 38 is 77, I think. So I have this expression. But 158 is 782 minus 312 times 2. So this is 312 times 39 minus 158 is 782 minus 312 times 2, all times 77. So what do I have? I have 312 times 39 and plus 2 times 77 times 312. So 2 times 77 is 154 plus 39. So if everything is correct, this is 193 times 312. You have to check my arithmetic, but hopefully it's not too far off. Minus 782 times 77. But 312 is 1876 minus twice 782. So this is 1876 minus 782 times 2 times 193 minus 782 times 77. So I have 1876 times 193, and I have minus 782 times 2 times 193. 2 times 193 is 386. And here I have minus 782 times 77. 386 plus 77 is 463. So this looks like minus 782 times 463. And finally, we come to the end. 782 is 4534 minus 1876 times 2. So this is 1876 times 193, and 782 is 4534 minus 1876 times 2, all times 463. So this is some linear combination. This is, I have 1876 times what? 193 minus times minus is plus 2 times 463. So 463 times 2 is 926 plus 193. Looks like maybe 1,119, and minus 4534 times I just can't read my own writing. It looks like 463. So, okay. So if the arithmetic is correct, it's correct, and I will check it exactly. Let's see.
It's correct, Professor. I checked already.
Oh, okay. So anyway, so that's what you do. It's it just takes a little bit of work and a lot of arithmetic, and it's almost impossible to do this without making a mistake. which is why you have to check every step and check the final result at the end. I mean, you just really have to like take your computer, your calculator, multiply this out, subtract, and make sure you get 2. So it's a kind of complicated way to write 2, but 2 is equal to 1,876 times 1,119 minus 4,534 times 963, or 463, whatever this number is. But that's what you do.
Professor,
Yes, sir.
I have a question.
Go ahead.
Can you do question 10 from 1.3?
Sure. Let's take a look.
Thank
So
you, Professor.
homework, section 1.3, problem 10. We have a simple continued fraction, A0, A1, A2, up to A sub n, which means A0 plus 1 over A1 plus 1 over A2 and so forth, till you finally get to the last step. So you have this somewhat complicated fraction. And we define 2 sequences of integers. So you have P0 is A0. P1 is A1, A0 plus 1. Of course, A0 is P0, so that's the same as A1, P0 plus 1. And for n going from 2 up to capital N, P sub n is defined in terms of the previous values of the p's, so-called recursive definition. This is an, it's the nth term of the continued fraction, times Pn minus 1 plus P sub n minus 2. So this defines a sequence of integers P0, P1, P2, P3 up to P sub capital N. And then we also define a sequence of integers Q0, Q1, and so forth. So Q0 is 1, Q1 is A1, and for n going from 2 up to capital N, Q sub n is defined to be an Qn minus 1 plus Qn minus 2. So these formulas are very similar. Here you just replace the p's with the q's, but the difference is in the first 2 terms, how you start the sequence. Here the sequence starts A0, A1, A0 plus 1. Here the sequence starts Q0, A1. And we want to prove that if you take the simple continued fraction, not the whole thing, just the terms from A1 up to A sub little n, this is always equal to Pn over Qn. So let's prove it by induction on little n. So when n is 0, our continued fraction is just A0, which is equal to A0. And what is P0 over Q0? P0 is A0 and Q0 is 1. A0 over 1 is A0. So these are equal. So that's correct. What about n equal 1? Then the continued fraction is A0, A1, which is A0 plus 1 over A1. if you put this over a common denominator, this is A0, A1 plus 1 over A1. But A0, A1 plus 1, this is P1, and Q1 is A1. So this is also true for n equal 1. Right? That is A0, A1 is P1 over Q1. Let's do the next case just to get an idea of what's going on. What is the simple continued fraction A0, A1, A2? That's A0 plus 1 over A1 plus 1 over A2. So let's just work out what this fraction is. This is A0 plus 1 over, this is A1, A2 plus 1 over A2, which is A0 plus A2 over A1, A2 plus 1. And if you put this over a common denominator, this is, the denominator is A1, A2 plus 1, and I get A0, A1, A2 plus A0 plus A2. Now, how does that compare to, we want to show this is equal to P2 over Q2. So what is P2 and what are P2 and Q2 equal to? Remember, here was the recursion formula. P2 is A2 P1 plus P0. And P1 is A1 A0 plus 1. And P0 is A0. And Q2 is A2 Q1 plus Q0. Q1 is A1 and Q0 is 1. So P2 over Q2 is this. Let me just keep it in that form. A2, A1, A0 plus 1 plus A0 over A2, A1 plus 1. But what did we find that our continued fraction was? A0, A1, A2, this continued fraction, it was this, A0 plus A2 over A1, A2 plus 1. When you put this over over the common denominator, A1, A2 plus 1, and here is A0 times A1, A2 plus 1 plus A2. Oops. Is that A2? What's wrong with this? Something in the middle. It's almost correct. Somewhere I interchanged A0 and A2. So let me just double check. A0, A1, A2 is A0 plus 1 over this, which is A1, A2 plus 1 over A2, which is A0 plus this, which is A0 times A1, A2 plus 1. I'll just keep it like that, plus A2 over A1, A2 plus 1. All right, that's correct. And P2 is A2 P1. It's A1 A0 plus 1 plus A0 so this is A2 A1 A0 plus A2 plus A0, and if I expand this, that's exactly what I have here. And yeah, so this is P2 over Q2. Right? So I'm just doing this calculation to try to understand what's going on. So the statement is true for n equals 0, 1, and 2. And so let's do a proof by induction. Let n be some number less than capital N minus 1, and assume, yeah, let me do it slightly differently. So let n be less than or equal to capital N, and assume the statement is true for the number n minus 1. So what that means is that the fraction a0, a1 up to a sub n minus 1 is equal to Pn minus 1 over Qn minus 1. No matter what these numbers are, they're just positive numbers in the continued fraction. They don't have to be integers, they can be any positive numbers. So let's write this out exactly. So this continued fraction a0, a1 up to a sub n minus 1, that's Pn minus 1 over Qn minus 1. This is a sub n minus 1, Pn minus 2 plus Pn minus 3 over an minus 1, Qn minus 2 plus Qn minus 3. So that's exactly our assertion for n minus 1. Right? So, I mean, there's a lot of writing here, and maybe I'm going, I should stop along the way. And let me ask whether, are there any questions about any of this? The first question is, the first thing you have to understand is just what this means, these definitions, these recursive definitions of Pn and Qn, and how this statement is correct, because I work it out in detail for the first three cases, n equals 0, n equal 1, and n equal 2. All right. So are there any questions about this? So then I'm going to assume it's true for some number, and I want to prove it's true for the next number. So assume, take some number, little n, no bigger than capital N, and assume the statement is true for n minus 1. That means this is true. This is true. And now we make the following very important observation, that if I take the continued fraction a0 up to a n minus 1 up to a sub n, what is that? That's a0 plus 1 over a1. And we keep going, we get 1 over a sub n minus 2 plus 1 over a sub n minus 1 plus 1 over a sub n. And if I look at this, let me just call that a sub n minus 1 prime. This is exactly what I would get if I took the continued fraction, but I replaced an minus 1 and an with just an minus 1 prime. I get exactly this. So I can write this n term continued fraction as an n minus 1 term continued fraction. I mean, this only makes sense if you worked out by hand a lot of examples, so you really understand what this continued fraction apparatus looks like. So a0, a1 up to a sub n is the same as a0, a1 up to a sub n minus 1 prime. So that's going to be, I'll call it P sub n minus 1 prime over Q sub n minus 1 prime. Just the rational number constructed from these guys. This is equal to a sub n minus 1 prime, P sub n minus 2 plus P sub n minus 3. That's our formula for n minus 1 over a sub n minus 1 prime, Q sub n minus 2 plus Q sub n minus 3. That's the induction hypothesis. That comes from the statement that our what we're trying to prove is true for n minus 1. But we use the fact that a sub n minus 1 prime is a n minus 1 plus 1 over a n. Let's substitute that into this. This is a n minus 1 plus 1 over a n times p sub n minus 2 plus p n minus 3 over a n minus 1 plus 1 over a n q sub n minus 2 plus q sub n minus 3. Let's just multiply through by a n to clear the denominators in the numerator and denominator. I get a n, I'll do it in several steps, a n minus 1, a n times a n minus 1 plus 1, p n minus 2 plus a n p n minus 3 over a n minus 1 plus 1 q n minus 2 plus a n q n minus 3. And then let's just remember our definitions. Pn is a n p n minus 1 plus p n minus 2, and q n is a n q n minus 1 plus q n minus 2. So let's see, what do I have here? I can factor out an an. I have an times an minus 1 pn minus 2 plus pn minus 3 plus pn minus 2. And if I factor out an an in the denominator, I get an minus 1 qn minus 2 plus qn minus 3 plus qn minus 2. And this is pn and this is qn. So this is an pn. So this is an pn minus 1 plus pn minus 2. And this is an qn minus 1 plus qn minus 2, which is exactly pn over qn. So we're done. But I mean, this is not a trivial problem. I mean, you actually, what you really need to do, I mean, we're using nothing more than high school algebra. We're just dealing with fractions. It's just complicated. And sometimes things are complicated. So anyway, that's a proof of the homework problem. Any questions about that? I mean, it may seem overwhelming, but this is kind of mathematics you have to learn when you take a 300 level math class.
Professor,
Yeah.
at the beginning, I think you said that you're gonna do it by induction, but didn't really say in what part you use the induction step, where you use the thing that you assume to.
I'm sorry, can you speak? The audio is, at least where I am, is very bad. So could you just start again and speak a little bit louder? Because I'm having trouble hearing you.
Okay, can you hear me now?
Yes, that's better.
Okay, so what I was saying is at the beginning it says that it was approved by induction, but I didn't like catch the part where you use the thing that you assumed to.
Okay, so all right, so I proved it first for 0, 1, and 2. And then I said, assume it's true, the statement is true for n minus 1. That means if you have a continued fraction, a0 up to an minus 1, that's pn minus 1 over qn minus 1. So this is the induction hypothesis. We're assuming this is true for n minus 1. Okay. And now we want to prove it. So here we're going up to n minus 1. Now I want to prove it for a continued fraction that has one more term. So instead of stopping at n minus 1, it goes up to an. And this continued fraction looks like this. But then I said, but if you look at an minus 1 plus an, and if I just call that an minus 1 prime, this continued fraction of length n is the same as a continued fraction of length n minus 1, where you just replace an minus 1 with this an minus 1 prime. So that was the inductive step. And then, right, and then I applied the formula to this and did a lot of algebra and proved the result.
Oh, got it. Got it. Thank you, Professor.
Professor,
Yes.
question 12 is related to that question. Can you go over that question too?
So let me put that off for a little bit because I want to make sure I cover the topic of the lecture. And then if there's some time at the end, I'll come back to it. And if there's not time, then I'll do it the first thing on Wednesday, okay? But I want to make sure I stay on schedule, basically. So,
Okay, thank you.
so I'll come back to it. And if I forget, please remind me because I forget everything anyway. So that's.
Are you going to the office hour today?
No, I can't today. I'll have office hours probably. I plan to have 3 office hours this week. I could have an office hour this evening, but there'll be an office hour Tuesday, probably Tuesday, Wednesday, and Friday. Combination of morning and evening, sorry, afternoon and evening to fit different people's schedules.
Okay, don't
Right,
worry.
but I have some medical appointments this afternoon and I won't be here, so I just can't do it today. Okay. Section 1.4 is called the fundamental theorem of arithmetic. So you know it's important because it's called the fundamental theorem. And it has to do with prime and composite numbers. So a prime number, which has been studied by mathematicians for thousands of years, is an integer p at least 2, right? An integer strictly greater than 1 whose only positive divisors are 1 and p. And a composite number is an integer n, again, it has to be at least 2, that has a divisor d such that d is strictly between 1 and n. And the number 1 is neither prime nor composite. Right? So if you start making a list of the integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, this is neither prime nor composite. But 2 is prime. The only positive divisors are 1 and 2. 3 is prime. But for 4, 2 is between 1 and 4, and 2 divides 4. So this is composite. 5, the only positive divisors are 1 and 5. So this is prime. 6 is composite. Because, for example, 3 is a number between 1 and 6, and it divides 6. 7 is prime. 8 and 9 are composite, both. 9 is divisible by 3. 8 is divisible by 2 and by 4. You just need 1. So for the first 9 integers, 9 positive integers, we have 1, 2, 3, 4 prime, 1, 2, 3, 4 composite, and the number 1 is the number 1, which is neither prime nor composite. And just some other notation that's important. D vertical line n means D divides n. And if D divides n, then n is D times something, call it D prime. That's what divisibility means, where D prime is n over D. And this is called the conjugate divisor of D. So for example, if you take n equal to 36 and D equal 9, the conjugate divisor is n over D, that's 36 over 9, that's 4, right? Because 36 is 4 times 9. So for the divisor 9, the conjugate divisor is 4. If you took D equal to 4, the conjugate divisor would be 9. There's a symmetry there. So this is all sort of basic notation. And we can make one quick observation that's important. If D is a positive divisor of n, and so n is equal to D times D prime, with, let's say D is less than or equal to D prime. That is, if you have two numbers, one's less than or equal to the other, then n, which is D prime, D prime is bigger than D. This is greater than or equal to D times D, or D squared. Which means, if so, D squared less than or equal to D implies, sorry, D squared less than or equal to n means D is less than or equal to the square root of n. So if n has a divisor D with D, so if n is composite, so if n has a divisor D with D greater than or equal to 1, then n has a divisor D which is less than or equal to the square root of n and greater than 1. So all this says is, if a number is composite and you factor it into D times D prime and pick that D be the smaller of the two factors, D prime is at least D times D, or D squared. So D is less than or equal to the square root of n. And square root of D is bigger than square root of 1, which D is greater than 1. So if a number is composite, it has a divisor no bigger than the square root of the number. And just one more definition. D is a proper divisor of n if D is a divisor of n and D is between 1 and n. So a number is composite exactly when it has at least one proper divisor. Any questions about this? I mean, it's a very good exercise. Which everyone should do for fun, or just to get a feeling for this, is find all the prime numbers P, let's say up to 100. So look at every number up to 100 and find all the ones that are prime. Well, you might say, well, that's a lot of work because there are 100 numbers to look at. But of course, up to 100, half the numbers are even. And except for 2, no even numbers are prime, because every even number is divisible by 2. And if the number is bigger than 2, 2 is a proper divisor. And you also don't have to look at 1. So you just have to look at the odd numbers. So you already reduced the labor by a half. And the prime numbers are central in number theory because every positive integer is a product. You can always break it down into a product of prime numbers. And not only that, except for order, uniquely. Except for order means the following. Take the number 6. It's a product of primes, 2 times 3. It's also a product of primes, 3 times 2. What I mean by saying uniquely is that if you have 2 factorizations of an integer into a product of primes, you can always rearrange the factors so that they're exactly the same. That is, there's a one-to-one correspondence between every prime here and every prime here. So 2 times 3 equals 3 times 2. These are different factorizations into primes, but they're not essentially different. They just differ by some arrangement of the factors. Or if you take a number like, I don't know, 1001. So here, spend a minute with a piece of paper and a pencil and determine whether 1001 is prime. And if it is, you're done. But if it's composite, then write it as a product of primes. Yeah, that's worth trying to do. I mean, you can start always by trial divisions. It's certainly not divisible by 2 because it's odd, but maybe it's divisible by 3 or 4 or 5 or 6 or 7 and so forth. Just kind of keep on trying. But if the fundamental theorem of arithmetic is correct, or the statement I just wrote down is correct, if every number is a product of prime numbers, of course, one factor is the product. I mean, it's either prime or a factor of 2 or more primes. So maybe it's prime, or maybe it's a product of primes. So is this a prime number?
No, it's divisible by 11.
Okay, so how do you write this as a product of prime numbers? What is the factorization? So you said 11 times something.
91.
Uh-huh. So is 11 prime?
Yes.
Is 91 prime?
Yes.
Uh-huh. Any other possible answers to this question?
11 times 3 to the 4.
3 to the 4th. 3 to the 4th is what? Let's see, 3
81.
times 3
Oh,
is-
I'm sorry. Sorry.
3 to the 4th is 81.
Yes.
So is this the prime factorization?
Yes.
Let's see. 91, it's not divisible by 2 or 3 or 5. Let's see, 7 into 91 goes 13 times.
Right.
It's actually 11 times 7 times 13. That's the prime factorization. 91 actually factors into 7 times 31. So when you factor, I mean, this is a correct statement. 1001 is 11 times 91, but 91 is not a prime. 91 is a product of 2 primes, 7 and 13. But this is the factorization of 1001. So anyway, number theory is worth playing with some numbers, and that's actually kind of a very interesting number because it's not obvious that it factors, and once you factor it, it's not so obvious how it factors, but that's the factorization. And by the fundamental theorem of arithmetic, except for writing this in these numbers in different orders, like 7 times 11 times 13, it's the only way to factor 1001. Okay, so the goal is to prove the fundamental theorem of arithmetic. And the first step is something called Euclid's lemma. Not surprisingly, because you find it in Euclid, which is a book written 2,500 years ago. So if you think you're doing modern mathematics right now, the ancient Greeks did this. So Euclid's lemma says the following, that A, B, and C be integers if A divides the product B times C, and if the greatest common divisor of A and B is 1, then A divides C. So let's write a proof of this. A divides BC means BC is A times Q. For some integer Q. And A and B relatively prime, greatest common divisor 1, implies there exist integers X and Y such that AX plus BY is equal to 1. So let's take this equation and multiply it by C. C is ACX plus BCY. I just multiplied by C. And BC is A times Q. So this is ACX. I replace BC with AQ, I get AQY. And then I can factor out an A. So C is A times something. So A divides C. That's the proof. So if A divides a product of 2 integers and it's relatively prime to 1, then it divides the other. And you can extend this there is a kind of converse. So if A is relatively prime to a number B1 and A is relatively prime to a number B2, then A has to be relatively prime to the product. Because if there was a common divisor of A and B1 and B2, you would have to divide one or the other. Yeah. So let me say that more carefully and in a somewhat more general setting, or just to extend it. So this is in the text, what is theorem 1.8? Suppose I have k at least 2 and integers a, and then k numbers b1, b2 up to b sub k. So the theorem says if a is relatively prime to each of these integers b1 up to bk, if a and bi are relatively prime for all I from 1 up to k, then A is relatively prime to the product. So the proof is by induction on K. And we'll start with the case K equal 2. So that A and B1 and A and B2 be relatively prime. And suppose we let D be the greatest common divisor of A and B1, B2. So this says that D divides A if D divides B1, then D is a common divisor of A and B1. But the greatest common divisor of A and B1 is 1. So if D also divides B1, then D is equal to 1. So D and B1 have to be relatively prime. Right? The only common divisor of D and B1 is 1. So what do we know? We're told that D is the greatest common divisor of A and B1, B2. So D divides B1, B2. D is relatively prime to B1. So by Euclid's lemma, D divides B2. Yeah, let me just start this again to make sure it's not so complicated. So I want to prove the statement for k equals 2. So that means if you have numbers B1 and B2, and A is relatively prime to B1 and relatively prime to B2, then I claim it's relatively prime to the product B1 and B2. So let D be the greatest common divisor of A and B1 and B2. So D divides A. If D also divides B1, then D would be a common divisor of A and B1, and the greatest common divisor of A and B1 is 1. So if D divides B1, then D and B1 are relatively prime. Right? We know that D divides B1, B2. That's our hypothesis. So D divides B1, B2. It's relatively prime to B1. Therefore, it has to divide B2. So D divides B2. D also divides A. A and B2 are relatively prime. So D equals 1. That's what we wanted to prove. If B1 and B2 are relatively prime to A, the product is also relatively prime to A. So suppose we take a number K at least 3. This is again a proof by induction, and assume that the theorem is true whenever we have K minus 1 numbers. So what we know is that A and BI are relatively prime for I going from 1 up to K. So in the case for K minus 1, we have that A in the product of these first K minus 1 numbers are relatively prime. But we also know that A and BK are relatively prime. This is one number, this is one number. The theorem is true when you have two numbers. That was the K equal 2 case. So A in the product, B1 up to BK minus 1 times BK is equal to 1. So that's the proof. That's the proof. And the important consequence of that for us is the following. This is theorem 1.9. If a prime number P divides a product of integers, then it divides one of the factors. So let P divide a product of K integers, B1, B2, B3, up to B sub K. Now, by the theorem we just proved, 1.8, the greatest common divisor of P and B sub I has to be bigger than 1 for some I between 1 and K. Because if P were relatively prime to each of these integers, it would be relatively prime to the product. But P divides the product, so it can't be relatively prime to each of them. P has to have a greatest common divisor with at least one of them, B sub I. Call that greatest common divisor D. D divides P, and D is greater than 1. So D equals P because P is a prime. The only positive divisors of a prime are 1 in itself. So if you have a divisor of a prime which is bigger than 1, the divisor has to equal to the prime. So P divides B sub I. And that's the proof. All right. So now we come to one of the high points of the course, and a theorem we use over and over and over again. I'll just write FTA, which stands for the fundamental theorem of arithmetic. Every positive integer can be written uniquely up to order, that just means 2 times 3 is the same as 3 times 2, because it's just an ordering change in the 2 primes, can be written uniquely up to order as the product of prime numbers. And the proof, well, this proved the existence of a factorization into primes. So we can do this by induction. 1, you can think of as the product of no primes, but if you don't want to worry about 1, 2 is equal to 2. It's a product of 1 prime. 3 is equal to 3. That's a product of 1 prime. 4 is equal to 2 times 2. That's a product of primes. 5 is equal to 5 is a product of primes, and so forth. So at least for the first integers 2, 3, 4, and 5, it's a product of primes in at least one way. So let n be at least 2, and assume every integer less than n is a product of primes. We have to prove it's true for n. So there are 2 cases. Case 1 is simple. N is p as a prime. You're done. N is a prime. It's a product of 1 prime. Case 2, n is composite. In that case, you can write n as d times d prime, where d and d prime, not necessarily distinct, are strictly between 1 and n. So you have a factorization. N is d times d prime. D and d prime are less than n. So by the induction hypothesis, d and d prime are products of primes. You just write n as a product of the primes and d times the products of the primes and d prime, and you're done. Okay. It's like saying, all we're saying is something like the following. Suppose I take n to be, I don't know, 1,260, which I can factor. It's 30 times 42. And 30 is a product of primes. It's 2 times 3 times 5. And 42 is a product of primes. It's 2 times 3 times 7. So this is 2 times 3 times 5 times 2 times 3 times 7. This is a product of primes, 6 primes, 2 2s, 2 3s, a 5, and a 7. That's all we said in the proof. If a number factors into d and d prime, and d and d prime are both products of primes, so is n. That's all we're saying. So that's the proof of existence. What's more complicated is to prove the uniqueness up to order. So must show that if n is a product of primes in one way, p1, p2 up to p sub k, and also equal to a product of primes in another way, say p1 prime, t2 prime up to p sub l prime, then the number of primes on each side, k and l, are the same. And there is a permutation that just means a rearrangement, sigma, of the numbers 1 up to k, such that P sub I is P sigma of I prime for all I equal 1 to k. So for example, if you had k equal 2, and you write 6 as 2 times 3 or 3 times 2, this would be P1 and P2. This would be P1 prime and P2 prime. If you let sigma of 1 be 2 and sigma of 2 be equal to 1, then 3, which is P1 prime, is equal to P2, but sigma of 1 is 2. This is P sigma of 1 prime, right? Equals P2. Oops. Sigma of 2. Three is P2, and it's also P1 prime. So P2 is P prime sigma of 2. Sigma of 2 is 1, and P1 prime is 3. That's correct. Okay, so how do we prove this statement? So I have n is P1 up to Pk, but also P1 prime up to P sub L prime. So let's look at the prime Pk. Pk divides n. So Pk divides the product P1 up to P sub L prime. And I just proved that if a prime divides a product, it divides one of the factors. So Pk divides, I'll call it P sub j naught prime for some j naught between 1 and L. But if a prime divides another prime, they have to be equal. So if I take n divided by Pk, that's the product of the first k minus 1 primes, P1 up to P sub k minus 1. And that's the product of all these primes, but you're dividing out by P sub j naught prime. That one's sort of omitted. And this is a number less than n. It's n divided by Pk. So by the induction, so I'm assuming, again, everything we prove is by induction. I'm assuming the statement is true for integers less than n. This number is less than n, so it follows that k minus 1, the number of primes here, equals L minus 1, the number of primes here. So k equals L. So these are, so you have the same number of primes on both sides of this equation, and one of these is a rearrangement. So this is a rearrangement of this. So there's some permutation, sigma, that takes these k minus 1 numbers to these k minus 1 numbers. And that's the proof, except for the fact you really need to study this line by line and word by word to understand what's going on. So everything I wrote down is correct and complete, but to understand it really requires a lot of work on your part, I think. So from the fundamental theorem of arithmetic, every number factors into a product of primes. And I mean, let's see. What's an example of a good number? $4,200. So a lot of people did this in elementary school. You had a number like 4,200 and you want to factor it. So you do like sometimes a factorization tree, like maybe this is 42 times 100. And 42 is 6 times 7. 7's a prime, but 6 is 3 times 2. 100 is 4 times 25. 4 is 2 times 2, and 5 is 5 times 5. And now all of these numbers are primes. And 4,200 is 2 times 2 times 2 times 3 times 5 times 5 times 7. So I have 1, 2, 3, 4, 5, 6, 7. 4,200 is a product of 7 primes. I can write 2 times 2 times 2 is 2 to the power 3, 3 to the power 1, 5 to the power 2, 7 to the power 1. So in the factorization of 4,200, there are 3 2s, 1 3, 2 5s, and 1 7. And we have a standard notation for these exponents. It's like, take the number 4,200. V sub 2 of 4,200 is the power of the highest power of 2 that divides 4,200. That's equal to 3. V3 of 4,200, that's the highest power of 3 that goes into 4,200. That's 1. V5 of 4,200 is 2, because they're 2 5s that divide 4,200. V7 of 4,200 is 1. And for every prime p bigger than 7, the highest power of that prime that divides 4,200 is the 0th power. Because this is also like 11 to the 0, 13 to the, I'm just running down the prime, 17 to the 0, and so forth. So if a prime doesn't divide the number, then VP of that is 0. So in general, for P prime and N, a positive integer, VP of N is the highest power of P that divides N. So here I can write 4,200. This is the product. That's what this capital pi means, of all the primes dividing N, P dividing 4,200 of VP of 4,200. And the standard notation from the fundamental theorem of arithmetic is every number N is a product over all primes dividing N, P to the VP of N, or I can write this as the product of over all primes, P to the VP of N, where VP of N is 0 if P does not divide N. Yeah. So it's a really important exercise or practice. To factor integers. I don't know. Like 1001, we saw was 7, 11, 13. You could write that as 2 to the 0, 3 to the 0, 5 to the 0, 7 to the first, 11 to the first, 13 to the first, 17 to the 0, 19 to the 0, and so forth. So VP of 1001 is equal to 1 for P equal to 7, 11, or 13, and VP of 1001 is 0 for all other primes. I don't know. 896. Let's see, factor 896. Just a random number. Write it as a product of primes. Let me know what you get. What is the factorization? Thoughts on the subject? What's one prime, divides 896?
2 to the 7 times 7.
Excellent. So this is 2 to the 7th times 7. So V2 of 896 is 7. V7 of 896 is 1. V3 of 896 is 0. V5, because 3 doesn't divide 896, and 5 doesn't divide 896, so V5 of 896 is 0, and so forth. So, but this is the factorization. It's kind of pretty. All right, well, there's a lot here to digest. But it is the fundamental theorem of arithmetic, which means it really is important. According to our syllabus, Wednesday is a review day, which means I'll review and maybe expand a little bit on the fundamental theorem of arithmetic and work problems. If you follow the syllabus, you'll see that the first exam is in about 3 weeks. It's on Wednesday, October 6th, and it covers all of chapter 1 that we do. But So just keep that in mind. Don't let it sneak up on you. Okay. Any questions before we quit for the day?
I have a question, Professor.
Yeah, go ahead.
I saw in the book, in the lesson, like there's also like a basically formula for the BP. Like if you have like a 10 factorial, you could find the B for the specific prime number less than less than n.
Right.
How that works? Like, is something like using the floor function? I didn't understand too much about it.
So right. So let me talk that takes a longer explanation, I think. And I don't know whether that was a homework problem, but what you're pointing out is that there's the following formula in the text, which is that the power of P that divides n factorial. Well, what is this? N factorial. So there's the following rule. If you have a product of two integers, VP of m times n, this is VP of m plus VP of n. So this is a homework problem to prove that. And then this implies that if you take n factorial, which is 1 times 2 times 3 up to n, the product of the positive integers up to n, VP of n factorial is the sum of, so that's VP of 1 plus VP of 2 up to VP of n. That's exactly the formula that you're asking about. Summation m goes from 1 up to n, VP of m. So this formula for the power of a prime that divides n factorial is a consequence of this sort of addition formula for VP of n. And this is one of the homework problems, which if you ask, I will go over on Wednesday also.
Okay, thank you, Professor.
Sure. Okay, anything else? If not, then we're done for the morning. Be well.